So thanks everyone for coming to this webinar. You can see the title from design to tape out verification for fabrication-ready PICs using Luceda IPKISS. Today it's all about fabrication and verification. So DRC, LVS, and how we ensure that people make the best designs they can. Quickly, I'll introduce Luceda and myself, and then I'll hand over to our speakers today. It should be an interesting webinar. I'm Matt Delaney. I'm the business development manager for Luceda up in North America. And I work with lots of foundries and customers here to ensure that their needs are met. Luceda, quickly, we're about a 12-year-old company, 11-year-old company, based out of the Belgian photonics ecosystem. We're about 50 people now, all in PICs, with offices around the world. We have an office in Shanghai in Belgium, as well as partners and resellers in other places. We have Spark in North America. We also are represented in Taiwan and Japan. And this is really the mission statement: to help photonic IC designers enjoy the same first-time right experience as electronic IC designers. And that's couldn't be more relevant to the content today. For people that are maybe not so familiar, IC designers, they live in this world where you can design a circuit, you can run simulations, run tests, and then you can fabricate it and usually have a very high yield and have it work on your first time round. We're not quite there yet with photonics. I think it's still fairly standard that people do multiple tape outs to optimize their parameters and sort of finalize their device designs. But really, that's what we want to look for. How do we want to do this? Well, there's sort of at least 4 aspects to it. The first is reducing design errors. These can be very costly in time and money. Tape outs are not cheap, as I'm sure you all know. We also want to leverage a single standard library. So our tool is built around Python. This allows us to bring in the Python ecosystem, but provide a centralized flow where everyone speaks the same language. We also obviously we want to design manufacturable PICs, and manufacturable is the keyword there. It's easy to make some very high-end designs, but actually, are they going to be able to be fabricated with the right tolerances, and will they work properly? That's where the foundry PDKs come in, and also the DRC, as well as just the knowledge and experience that the foundries bring to the process. And doing all of this, we want to improve the time to market. We want to reduce these iteration cycles, and really bring photonics to the market as quickly as possible. Very briefly, a quick look at our design platform. On the right-hand side, you'll see some of the different products we have. Luceda IPKISS is the core one. We also have products for designing AWGs, for managing IP and libraries, and also for an advanced circuit simulation. We have links with various commercial third parties such as Ansys, 𝗬𝗏𝗄𝗏, Flex Compute, etc. And then on the left, you see some of the design kits we have. And today we're joined by Tower Semi, who you'll see in the at the top in the middle in the silicon one. But it's also, there's a whole ecosystem around this as well, with packaging, test, assembly, and so on. Very quickly, the agenda for today, Tower Semi will have 10 minutes. They're going to introduce their leading PIC platform and focus on why DRC is important. And hopefully we'll hear from some of their sort of customer stories as well. Following that, Spark Photonics can give a brief introduction to themselves and also talk about how DRC fits into the PIC design flow as well as LVS. They'll also be covering Check Mate DRC, which is their custom tool. And then finally, at the end, we'll be giving a short presentation showing some of the new features we're bringing to Luceda, and some of the old features as well. So there'll be an LVS run, there'll be some DRC, and there'll be some error correction using functions as well. And then finally, at the end, there'll be 10 minutes for Q&A. So feel free to put your questions in the chat at any time, and we'll pick them up at the end. Or if you prefer, you can turn your camera on and join us in person as well. And then finally, I'd just like to introduce the speakers. From Tower Semi, we have Dr. 𝗟𝗂𝗰𝗲𝗏. He received a PhD in physics from the University of California, Riverside, with an area of expertise in graphene device fabrication and physics. He joined Tower Semi at the start of its silicon photonics program, and played a foundational role as the R&D process engineer. Today, he serves as the Director of Silicon Photonics Technology Development, where he leads the company's global R&D efforts to advance silicon photonic platforms and technologies. We also are joined by Dr. Sean Nealon from Spark Photonics. Sean holds a PhD in electromagnetics and photonics from the University of Delaware, and has a special focus on RF photonics design, simulation, and fabrication, particularly around Teflon devices, so thin film lithium niobate. He's now the engineering lead at Spark Photonics, and he leads the commercial projects involving the design and layout of high-performance silicon nitride, and Teflon structures, mostly centered around telecom, datacom, and quantum communication systems. And then our third speaker will be Dr. 𝗦𝗽𝗿𝗲𝗿. He has a PhD in photonics from the University of Southampton. He's worked at Luceda for 4 years as an application engineer, supporting our customers who use IPKISS, and also creating prototypes for customers, as well as building on webinars and examples. He uses his customer support experience and feedback from these customers to manage the internal products, or to help contribute. With that, I'd like to hand over to Dr. 𝗟𝗂𝗰𝗲𝗿. The floor is yours, and I'm looking forward to hearing what you have to say.
Great, thank you very much for the introduction. And first of all, thank you very much for the Luceda and Spark teams for inviting me. I'm very happy to kick off this discussion. I think it's very important, and it is something that the integrated circuit area is quite mature in, but for silicon photonics, there's still quite a lot of work to be done that Luceda and Spark are leading. So very happy to kick this off. Quick introduction to Tower Semiconductor for those who might not be familiar with us. We are a pure play analog foundry. We have a wide portfolio of analog technologies, the technologies in sensor, power devices, RF-SOI, silicon germanium, MEMS, and of course, the discussion that we're having here for silicon photonics. We have a wide array of wafer sizes from 8-inch to 12-inch in our manufacturing lines. And we have a global manufacturing footprint with manufacturing facilities in Israel, Europe, US, and Japan. Specifically, silicon photonics that we're going to be talking about today is done primarily, volume manufacturing today done primarily in Newport Beach, with rapidly bringing up silicon photonics production in our sister fab in San Antonio, Texas, and also 12-inch process in Uozu, Japan. We have a lot of activities in silicon photonics at Tower, but specifically the one that we'll focus on today and the one that's most mature and in highest manufacturing now is our PH18M platform. This is a 200 millimeter wafer photonic integrated circuit process. You start with SOI, silicon insulator starting material. We have modules to build silicon waveguides, strip and ridge-based waveguides. We have nitride waveguides, several implant layers to build silicon phase shifter-based modulators. We have access to germanium, leveraging on our long history of silicon germanium technologies and expertise to be able to build germanium photodetectors integrated directly in the PIC. And taking advantage of our CMOS VLSI manufacturing, we have a planar metal backend with several different options in terms of number of metals, metal thicknesses, and backend devices such as heaters, capacitors, termination resistors, and so on. We also leverage our experience in MEMS to be able to add deep oxide and deep silicon etches, in-fab deep silicon etches that create optically smooth facets, making the wafer suitable for fiber attach and edge coupling, supporting optical input and output. So why are we here? Why are we talking about the importance of verification? Well, since I'm talking from the fab side, from our point of view, and from the point of view of my fab managers and process engineers, they want to make sure that we can manufacture silicon photonics without introducing any additional danger to the fab or introducing any quality issues. One such example is, let's say, as a designer, you accidentally place a chunk of metal inside an area that is meant to be an edge coupler trench. This metal will cause several issues, but specifically from the fab point of view, it could expose our dielectric tools to to metal contamination and potentially effects that will damage the tool sets. Of course, fab will be very unhappy. This will lead to quite a few excursions and impact the overall productivity of the fab for this process and for other processes as well. Another important reason for verification is to ensure that the design, as designed, can be manufactured within the technology set that we're using. In this case, for example, one specific case from a very early design when we were just starting in silicon photonics and our DRC was not as mature as it is today, we had a customer design for silicon-based grating coupler with a design pitch that was beyond the capability of our lithographic tool sets. So of course, when the design comes out of the fab, the customer sees something like this and sees that none of their grating couplers are functional. So of course, that's not good for the fab. It's not good for the customer and can introduce long cycles of learning and additional churn on time to market. Whereas a similar design, but with design rule compliant spacing, now produces a grating coupler that can be resolved and can be manufactured in a reliable and consistent manner. So what is the solution to avoid these kind of catastrophic issues? Well, design rule verification, DRC. And that's, of course, the whole reason why we're here. From the customer point of view, similar motivation. Customer doesn't care so much about our fab. They, of course, want to see it running and have high uptime. But in their case, they're primarily interested in receiving devices as designed and functioning. So here, once again, their main concern is, will this feature that they've designed be reproduced as expected? Well, again, in these two examples, for example, a grating coupler here is clearly not reproduced as it was expected. So that's a fundamental issue for their product. And additionally, the customer would like to know whether the design will function as they expect it to function. This would be higher level design, higher level verification with LVS layout versus schematic. I'm not going to go into details here because the experts we have later in the panel are much more versed in these topics and will be able to give much more insightful feedback. So I think we all agree verification is important. So why are we here with silicon photonics? Tower, we've been doing electrical manufacturing, and the electrical infrastructure is very mature. DRC and LVS is very mature within those technologies. So why can't we just take what we have, what we know in electronic manufacturing, and apply it directly to the new silicon photonics technologies? Well, one very fundamental issue is the non-Manhattan geometry that's typically found in silicon photonics technologies. Traditional CMOS designs look something like this on the left. Everything is rectangular. Everything looks like effectively Manhattan, looks like skyscrapers. In this case, devices look similar, and DRC coding can be done in a more standardized and typical way. For photonics, because now we're dealing with waveguides, we're dealing with optical signals, the devices tend to look a lot more like these squiggles. And that can cause issues with traditional DRC and traditional LVS kind of designs and kind of coatings. Another challenge is in silicon photonics, it's a relatively early field, so there are many different applications where the same process can be used. We run into this situation quite often where the majority of our customers are in data center applications, transceiver applications. However, we get interest in tapeouts in many other applications like sensing, LiDAR, and many others. In this case, a device that is functional for a LiDAR application can look very different and can actually violate some of the device design rules that are built around the transceiver applications. And DRC has to be coded in such a way that it's not too restrictive to allow these new and different applications and novel devices while still being effective at catching catastrophic errors for fabrication and device operation. And finally, electronic ICs require only electrical input and output. For photonics, we need electrical input and output, but also optical input and output. This requires specific features, usually at the end of a process, and on layout areas that span between the customer design and scribe line area that is traditionally reserved for process control structures and other fab infrastructure. And this can make verification and scribe assembly very challenging in ways different than what exists in electrical circuits. So now to motivate this with a few common violations that we see and some examples that we've seen in the past. The very first one that's probably the most fundamental and the most challenging has to do with these curvilinear designs. How do you code DRC in a way that will distinguish intentional optically functional devices from layout errors? One example where this is seen is, let's say, an accidental jog is placed in a waveguide that will create a major scattering site and cause a major impact to the propagation properties of this waveguide. Well, if we contrast this with an intentional device like an MMI, the things that we can look for are these right angles. However, in a functional device, we still have the same kind of right angles that are intended for device functionality. However, in a waveguide, this will cause significant issues. So the DRC has to be smart enough to somehow to understand the designer's concept for a specific device and areas where to apply specific design rules. So, of course, this is bad, whereas this intentional device is fine. Line-on-line designs is also something that we see very often. One example is a modulator with a P&N implant. Many times designers will try to draw these two layers line on line. However, normal process variation will lead to these layers sometimes being overlapping, sometimes being underlapping. In that case, through normal process variation, we can get a PN junction in a modulator or a PIN junction in a modulator, leading to very different device performance on these devices. And then finally, going back to the point of different applications, we often find research devices or generally novel devices that violate design rules that we have in place meant for PDK devices or other devices that we know can fail, but these, for new devices, the design rules may not be applicable. So this is a challenge to separate and really understand what are the design rules that we can allow violations for versus ones that will be catastrophic for the manufacturing of the device. I think with that, I would like to end here and pass it on to Sean of Spark Photonics to give a designer's point of view on some of these topics.
Thanks, Oleg. Let me see if I can get my screen to share here. All right, everyone should be seeing my screen, but please yell at me if you can't. So, of course, thanks for the great overview, Oleg. You know, Tower, those guys are doing great things, and we use them quite frequently here at Spark, so happy to kind of continue this discussion. I wanted to provide sort of a perspective from the designer. And so for that, I'd like to start by introducing Spark and what we do here. So Spark Photonics is a pure play design and consulting firm. We offer design and consulting services for all things PIC related. I call it A to Z enablement, meaning if you know nothing about a PIC, you can come to us and say, you know, hey, I want this this PIC laid out. Let's choose a foundry, let's choose a packaging house, you know, do the design and tape it out, and we can enable that for you. Outside of that, we also do software and hardware. So of course, we are the North American support and distribution network for Luceda IPKISS. And we also offer photonic development PIC kits right now for AIM Photonics, but of course now we're expanding to other foundries as well. These offer some test structures that you can measure in a lab and kind of use to get exposed to photonics and what it does. Finally, we do education and outreach to try to get K through 12 and college students into photonics. Of course, we're in quite an emerging ecosystem here, and the more players, the better. So with that said, and with that perspective, I'd like to introduce, sort of what the photonic layout workflow looks like from our side, and kind of, cover why LVS and DRC is important to this flow. So imagine you're a company and you want to tape out a photonic circuit. Generally, we like to start with a schematic. In this case, the team doing the systems engineering or the general layout of the photonic circuit can sort of abstract small components, MMIs, waveguide transitions, things like that away, and give a nice overview of the bigger picture of that circuit, to the teams down the line. What this might look like is a chip frame with pads attached to it that you could say, this pad attaches to a PID controller, this pad is an RF connection for a modulator, and then virtual connections over to black boxes that might represent your modulators, a splitter tree, an AWG, things like that. This view is then organized for conceptual efficiency. And of course, what I mean there is a team could look at it and say, this is my transmitter, this is my receiver, this is a virtual waveguide connection showing that something's connected. Here's a block of edge couplers, whatever it might be. And to do this, we could use Luceda's Canvas tool. We'll show this in just a bit, but the Canvas tool allows us to very, very conveniently put together these schematics. And not only just assemble these schematics, but we can use this to simulate. We can do direct to code from the schematic. So for those of us who might not be as familiar with Python, not a problem. Just drag your circuits around, send it to the code, and you'll end up with the physical layout. So the physical layout is sort of the next step then of photonic layout. The team that might make the schematic can convey that circuit outline, that blueprint, to the team doing the physical layout. And that team performing the layout can say, okay, this is a modulator. I know that based on the schematic, I need a modulator in my layout, but this modulator might have more components than is represented in the schematic. For that, imagine I'm the team doing the layout. I could generate a cell that says, here's an MMI, here's an electrode, here's another MMI, and maybe a thermo-optic heater for bias control. So then we land at the physical layout. This is derived from the schematic, but it contains all of the physical components necessary to make the device. So then this is organized for physical efficiency. This could include, things like path length matching, correct bend radii, chip size considerations, things like that. But this physical layout is always derived from the schematic. So I don't want to go and add pads or add, different connections, maybe connect my modulator to edge coupler number 1 where it should be connected to edge coupler number 3. Which could cause massive problems for the people trying to package this PIC and connect it to their expected outputs and inputs. So then how do we actually confirm that the physical layout matches the schematic? In some cases, if you just have a few components, it's easy to look at it and say, yes, that looks like it matches, we're ready to go. But our tapeouts, especially for transceivers, for some quantum systems, these are getting more and more complicated to the point where we could have hundreds or thousands of components on a single wafer or a single reticle. So we want to find some convenient way to do design rule checking and layout versus schematic checks on our schematic and our physical layout to make sure that these things match up to the point of, everything is connected, there's no waveguide gaps, such that we can submit our design to a foundry like Tower. And number one, Oleg won't come back and yell at me and say, hey, all of your waveguides are mismatched and you have metal layers on your trenches. But also when I get this submission back and I have a packaged chip that I know if I send light into edge coupler number 1, it will go through my thousands of components and come out at edge coupler number 10. And so for this, once again, we can use Luceda, who will, in just a bit, show some great examples of layout for schematic. But here at Spark Photonics, we've developed Check Mate DRC, which is a automated tool to perform design rule checking. And this is integrated right into IPKISS. So with one extra line of code, you can say, hey, I wonder if my P cell or if my layout is design rule check clean. So it's super easy. From there, once we've performed our DRC and our LVS and we've ensured that our layout is what we expect it to be, we can send it over to Tower, and Oleg will not send me an angry email asking me to change lots of things. So with that, quick introduction of what Check Mate DRC is. So here I've tried to outline what I call the legacy DRC process. The legacy process here involves me as the designer saying, okay, let's use my layout tool, in this case Luceda IPKISS, to create my circuit, but then a separate tool to perform the design rule checking of that circuit. In this case, these tools might not be linked together. They might not talk to each other. And so there might be a very different workflow for designing or sending my circuit to that DRC tool versus just calling some sort of tool directly on the layout that I've created in my actual layout tool. Moreover, these tools can be a bit clunky in that sense, difficult to use and extremely expensive. So our thought then was, what can we do to integrate some sort of design rule check tool directly into Luceda IPKISS in a way that it doesn't add hours to my day to run DRC on my layout. I'll be more motivated to run it as I go rather than just at the end and then have to change everything. And so for that, we introduced Check Mate. So Check Mate is a tool that can run independently, but can also be integrated directly into IPKISS, such that when you generate your layout using IPKISS, you can add one extra line of code to say, all right, Check Mate, run a DRC check on my layout. That's an immediate return. You'll get a 𝗟𝗰𝗲𝗿 report database file where you can open that up and say, here's all the problems. Easy to see, let's fix them right away, rather than having to go between two tools that are perhaps unrelated and difficult to navigate. So at the end of that, I'm much happier than I would be if I'm using clunky tools that add hours to my day. A quick example then, how does it work when I'm running it from IPKISS? In this case, I have my layout. My layout is a simple circuit comprised of two components, component 1 and component 2. I'm placing these components, but I've placed them too close together. And this is a problem. And so you can see then, the second to last line, I send my layout to a GDS file, and I just call it layout.gds. If I were to submit this layout.gds file to Tower, these components would be too close, and perhaps it would cause issues on the performance side for me, or perhaps it would cause process issues on their end. So instead of that, I can simply run DRC at the end of it. And again, a single command here that performs a DRC check on my layout and returns that 𝗟𝗰𝗲𝗿 report database file that I can view all of the issues and I can correct them in real time rather than guessing. Now, I mentioned that Check Mate can run independently, so it does have a graphical user interface here, which we've tried to make as convenient as possible. So you can open up this tool, you can choose from these various options. On the right side, I've tried to highlight a few of them. It's possible to select which layers you want to run your DRC on. Imagine you're designing a modulator with metal layers and optical layers, and you want to say, hey, I know, I'm halfway through my design. I know that the metal layers are going to have problems, but I just want to check the optical layers to make sure they work out well. in some cases we have a lot of layers, so we want to limit them and make the rules easier to view. So we can do that. In the same vein, we can select different rules if we're having an issue with one or of just a few of them. We can do that too. So that then brings us into photonic LVS, which is the kind of the other side of this, making sure that things are connected to what we expect them to be connected to, that there's no disconnects that we don't expect. And this is, another way of checking your circuit, but it's a bit different than DRC. So I wanted to give then a very quick introduction of what photonic LVS means in this case. And so, put simply, the two views of our layout are the schematic on the left side, and this represents the photonic circuit at the highest level. And again, it's organized such that you as the human can look at it, you can figure out what's going on, and you don't have to deal with, this lithium-niobate layer connects to a silicon nitride layer, and then that goes into silicon. It's just a single virtual connection, and it's easy to kind of understand. On the right side, the physical layout is, again, always based on the schematic in theory, right? And so that contains all of our physical layers, our real connections, our metal pads, our waveguides and modulators and all that. And that's organized for physical efficiency, or in other words, we try to optimize performance of real devices. But we want to make sure that these two things really are matched up, that the physical layout really is based on the schematic, and maybe I, as the designer, didn't make a mistake and connect a waveguide to something I shouldn't have. And so how do we do that? Well, we perform layout versus schematic. And in just a short while, Matthias will be showing that. But the concept here is essentially that our layout versus schematic check shows us or compares the physical layout to the schematic to say, hey, if there's a waveguide connected on the physical layout, that shouldn't be on the schematic. Or if there's, vice versa, something connected on the schematic that isn't on the physical layout, then let's highlight that as a problem and show the designer. In a similar sense, on the right side there, we have electrical connectivity checks. Maybe there's some disconnects there, or maybe there's some overlaps, whatever it might be. LVS will highlight that in a way that you can easily find the issues on your circuit with thousands of components, and so you don't have to go scrolling around and trying to visualize all these issues on your own. So with that, I'll hand it over to Matthias for a bit of a deeper dive into this concept. Over to you, Matthias.
You're muted, by the way.
All right, now you can hear me.
Yes, great.
Yes. So, hello everyone. So I'm Matthias Wijzen. I'm an application engineer at Luceda Photonics, and now I'm going to explain how you can use IPKISS for verification to make sure you can verify photonic design and make it ready for tape-out. So as my colleagues have already explained, I don't think you're seeing this. Yes. So as my colleagues have already explained, verification is a crucial aspect of the design process. It is needed to make sure that the design works as intended. So before we continue, an important note, some of the features presented in this webinar are currently under development and not immediately available. I mean, specifically in my presentation. So now let's see how verification fits in the design flow. So I see Sean has already presented this. So in photonics design, particularly for larger teams, it is typical to start from a schematic. And from the schematic, you start working on your layout. And once you have your initial layout, then you will see your verification in an iterative process. So if verification fails, you need to adjust either your layout or your schematic and run verification again. And once verification succeeds, you can move on to tapeout. So there are several different aspects of verification. So you have functional verification, which is to make sure that your design works as intended. So this includes layout versus schematic testing, also known as LVS, of course. And then you also include the circuit simulation and the corner analysis to check both the behavior of your device and to analyze its robustness to varying conditions. And then there's also physical verification, which is to make sure your design is physically realizable, and that's what DRC is. So now let's start with an example of a design made in IPKISS. So this is a 4x4 Bennett switch in the that was designed in the Tower PDK. So it consists of some 2x2 switches connected together as shown. So by changing the bias states of these switches, we can control where the light goes. So we start with a schematic design, which was made in IPKISS canvas. So I'm just going to show you what this is. So this thing's in the way, it's annoying. Now it's out of the way. So now I can show you our schematic in IPKISS canvas. So this is with Kansas, where you worked on our schematic, which has all these 2x2 switches connected together, as shown here. We can already start a simulation of our schematic. And basically, as you change these bias states, they would change where the light goes. And when you run your simulation, you will see indeed that you have all of the light arriving close to 0 dB at one of the output ports, and then at the other ports you have very little light, like less than -80 dB. That's in your initial schematic simulation. So this is, of course, the expected behavior, and so it's an initial verification you can do. And then once you've done that, you of course move on to the layout. So you export to an IPKISS code template, and then you work on your layout, and you'll eventually end up with an IPKISS layout that it will visualize. So this is now your layout of your Bennett switch in IPKISS. So this was done in the Tower PDK. So it uses the Tower layers and components. So you have this phase shifter here, which is in the Tower and you have your MI here. And this is, now you want to verify this. So we already worked on initial layout. This was done in our own that we coded. You want to verify that this layout works. So there's different aspects of verification. So one of them is to actually check that the light goes where you want it to using simulations. So you can see here, there's already have done some simulation of our device. This is using a tracer analysis, which is a new tool that is part of Circuit Analyzer. And you can see here by clicking on these arrows, the right at the output. So you can see here the result of a simulation sweeping the wavelength at the output of your port. So you can see here also these different arrows. So these actually show the light at these different locations. So if you have to click on this arrow, you will see the light at the output port of this MI. And then you click on this one, you can see there's a little bit of loss that appeared as it propagated through this. And then a little bit more loss as it appeared here. And so now we will continue. So there's other aspects of verification here. You can already start working on verifying more of this design. So actually, this is actually this layout. It's not yet exported to, it's not yet connected to grating couplers or to bond pads. And we are doing verification on our layout before we do this routing to make sure that it is in fact correct. But if we were to wait till a lot later on, they would actually be and that's having to really a lot more work potentially. So we do some verification on this layout. So we they actually have this part here is currently under development, is not getting the released version of IPKISS. We can detect design violations and visualize them inside of our visualizer. So this visualization inside of the visualizer is not yet in IPKISS, but one of these things you can detect for are layer overlaps. So this is already available in IPKISS, only in code, it's just not yet visualized. This allows you to see where you have a layer overlapping with itself. That can be something that it would actually could be a problem in this case, because we have two waveguides overlapping each other. So in this case, because they cross each other, you can see that your design does not actually work. So by checking for overlapping layers, you can check if your design would actually work or not. So in this case, you see that there are some overlapping layers with our waveguides overlapping. And here we're crossing over. So this is actually a pretty simple example, but it could actually be a lot less obvious if you tell a much larger design, which is why it's important to have this sort of verification. So now that you've detected these overlapping layers, you can move on to the next part. So we're going to fix this error by adding a crossing. So you can see this now, this new layout has occurred, that we added a crossing to our design. And we are going to also simulate this again. So we're going to see the tracer analysis show up again shortly. And it will show that we still have the light flowing where we expect it to. So we have the light inputted here. It still follows this path and arrives at the correct output. And but now we can actually see the effects of the loss of the crossing. So we have this arrow here, so it is not necessarily so clear. You can see, but this arrow here shows the light at the output of our NMI. We can see but they also have this light here. So this actually shows the light at the output of this crossing. So you can see out 0, that is actually the output port of the crossing. And this allows us to see the loss from both this waveguide section and the crossing. So you can actually estimate the loss resulting from the crossing. Let's open this a little bit. You can see there's actually a little bit of loss associated with the crossing, but overall our design still works as intended. So at the output over here, we now have the light still at this output. Now we see a design is 40 dB worth of light in the other outputs, and that's actually because of crosstalk that's been introduced by our crossing. But now we're able to detect this. And now we're going to continue with more verification. So there's other verification functions that are available in IPKISS. So if you take a look here, we are actually going to check for snapping error. So this is still under development. So this is a method that we have under development for detecting snapping errors inside of your layout, and we can also detect acute angles. So this is already available in IPKISS. You can already use it. It's just, again, not in the visualizer. This allows you to detect acute angles in your layout. So these are additional things you can verify to check if they are in your design. So here is looking for some snapping errors, and it's going through this. You can already see that I found a few of them. So these snapping errors are actually in the crossing. So if you can see here, and they are the result of the crossing being rotated by 45 degrees. So if you basically what happens is that when you export to your GDS, everything is snapped to the grid. So we're just going to show a bit in more detail this crossing. It's going to be easier to show. click this snap to grid, this emulates how this actually occurs. You can see this little snapping error here. And this is because of our crossing being rotated by 45 degrees and our waveguide here having being off having this these diagonal sections, and these cause the vertices of a crossing and of our waveguide to be off the grid. And because they are off the grid, this means that when they are snapped to the grid, there is a discrepancy between them. But this is something that we can actually fix in IPKISS. I'm going to show you how later on. That's one type of error. These are actually found in here. It finds that all these snapping errors at each of these crossing outputs. But you also have these acute angles. So if you were to re-add this layer, you can find that we have these acute angles in these locations. And these are also will cause an issue during fabrication, and are also therefore something that in most PICs, and therefore it's also something you can detect ahead of time to see if they occur in our layout. So, and now we have detected them, we're going to fix them. So I'm just going to show you how to fix them. I'm going to go back to the slides. So to fix a snapping error, you just need to apply selective flattening. So this is still in a prototype stage. So you have our crossing and we have our waveguides. We basically flatten just this part of our layout. So it becomes essentially like one component, or the elements become part of one component. And that means that when we export it to our GDS, you will no longer have this snapping error because they are all snapped as one component. And the other thing we do, we patch the acute angles. So I'm going to show in the code. I'm just going to run this code again to show this, but I'm also going to show how this is done. So this is, of course, a prototype, but this here are already part of IPKISS. It is very easy to automatically detect and add all the acute angles that you need to add to your design. And now you can see that if you zoom in, you can already see these acute angles have all been patched, which means there are no going to be any DRC errors detected when you run DRC on it. And if you snap to the grid, you'll find that these snapping errors are no longer there. So we managed to eliminate both of these types of error. And so now we're just gonna be rigorous. We're going to run everything on our verification. We're gonna run look for layer overlaps again. We're gonna look for snapping errors and for acute angles. So now let's take a look at this things over there. And we actually see that 0 layer overlaps, 0 snapping errors, and 0 acute angles. So that's and now we can see that these types of common layout errors that we can detect and fix using IPKISS have been resolved. We now move on to LVS. So what is LVS? So as Sean already gave a good explanation of what LVS is. But basically what you do, you compare two netlists. One netlist that is extracted from your GDS, one netlist that is extracted from the schematic. And you compare these netlists to find out if they are the same. So if they are the same, then your LVS test has succeeded. If they are different, then their LVS test has failed. So how do you do that? So first you have to export your GDS with some port metadata. So on each of these where you have a port of a component, you have to draw it on a pin recognition layer for the ports, and this has to include metadata with information about your ports. Then once you have that, you will have to then import GDS, you extract the netlist, you compare with your golden netlist from a schematic, and you run LVS, and then it will create a file which explains whether it's going to the two netlists are identical or not, and it provides information on if they're not. So I'm just going to demonstrate this. So you have LVS over here. So let's just run LVS. So it's going to create this file here. So just going to delete this and just run it again so you can show this file being created. So it's going to create this file with the information on the LVS. And it says, in this case, it says that the two netlists that it compares are identical. So it took the netlist from the schematic, it compared it with a GDS, I found them to be both identical. But let's say that we have a mistake in our layout. So let's say we forgot to implement a connection here. So let's run LVS again, see what happens. And so now we actually have some helpful warnings also. But inside this LVS.log file, it says that there are some nets inside of a netlist that's extracted from the GDS that are missing from your golden netlist that comes from the schematic. So you can see this. It says specifically that this connection here is missing between these two switches. So if you take a look on our GDS, we can actually take a look and see what is actually happening. So let's just open our GDS. So you can see now that you can indeed see that there is a missing waveguide, which we have detected now thanks to LVS. And in a much larger design, this might actually not be so easy to see, even in a. And now let's go back and we're going to fix our error. So, and now you're going to run this again. And now, so you fix this, and you look at our LVS file again, it says, again, these two netlists are identical. And if we check on our GDS, we see that now this waveguide connection has been fixed. And then afterwards, we've done LVS, we've done DRC. We can actually move on to routing it to the outside world. You can even run DRC already on that. But of course, we want to tape out. So we route it to the outside world. And then basically, it's going to show our visual of our routed chips. So now we can see that we have routed it to some bond pads here, some grating coupler, some bond pads and grating couplers here, and we are going to. You can see here that now we're going to have to export it back to a GDS. I want to run DRC on it in Check Mate. So as shown, so it is one single command to do so. And then you can just take a look inside of our, it will create a file, which is this file here, for example. So let's open our file. So we can also actually have it just open directly in KLayout. And we're just going to import from our this file in here. And basically in this file, it will have basically show all of them any DRC errors. And so in this case, I'm going to show you what it looks like. In this case, you see there are actually no DRC errors. And basically what we did either, while we were working iteratively on our design, we either fixed all the DRC errors that we detected, or we asked the foundry, that's Tower Semi in this case, because it's Tower Semi design, if this Tower DRC error could be waived. So that, since we can have it, I've found it to be free of DRC errors. We've tested LVS, we've done some circuit simulations. We can, in principle, send it to a foundry. In principle, though, there's also another thing you can do, which is called corner analysis. And this is actually shows you the effect of providing variations of your design. So when you do corner analysis, there are what you can do is take a look at this YAML file. So we have got a nominal case. We can actually take a look at the very effect of varying certain parameters of the circuit model of your components. So just take a look at how it behaves as you've done these variations, and this is actually something that allows you to check for the effect of fabrication imperfections, for example, and other things umbilically. It would allow you to see if, based on these any imperfections that you expect, that whether your design will still work. So in this case, you can see that based on the various imperfections that we anticipate, that we have kind of go up to like up to a bit more than minus 20 dB of stray light. But you can decide whether, but the overall functional behavior of your device is still what you within what you would expect with most of the light arriving at one particular port. So you can decide whether this is acceptable to you or not. If it is acceptable, you can tape out, and if it is not, you can decide to do something else. So basically, I showed you how in IPKISS you have various different methods for verification. On top of DRC and LVS, you can also do circuit simulation and corner analysis. That allows you to tape out. So now I'm going to actually ask if there are any questions. So sorry, I was a bit over time possibly, but we still have some time for some questions. So I'm going to stop sharing my screen and let's ask the audience for some questions.
Thanks, Matthias, and to all the other speakers. As I mentioned at the start, people, you can write questions in the chat or feel free just to speak up, whichever you prefer. Maybe I'll start whilst people are typing them. Oleg, I had one question for you, which was I've done a little bit of fabrication in my past, and often the reason for some of the DRC rules is to protect the tools. As you mentioned, you don't want contamination, or you don't want sort of small bits of silicon to flake off and float around your devices. Is there ever any conflict between the foundry wanting to protect the tools and the process and the customers wanting to really push the boundaries of their application space? And how do you deal with that?
Yeah, certainly all the time. It's generally a negotiation between specific tool areas, specific tool owners, if they think that there's a sizable risk, or if it's something that can be accepted. And yeah, it becomes, especially for silicon photonics, it does become a gray area where we often have to go through a device violation by violation and evaluate with a fab whether it's something that can be fabricated safely and therefore allowed at risk to the customer, or it's something that will cause a risk to the foundry and cannot be allowed.
Cool, thanks. And then Sean, maybe a quick question for you as well. I know in my work I use Canvas quite a lot as a communication tool. After a certain level of complexity, a GDS file becomes very difficult to actually interpret. In your work with clients, with customers, how do you manage the expectations? How do you translate their vision into a product and make sure that what you submit is actually the design they wanted? Because I imagine that's not always easy.
Yeah, that's a good question. I think it really depends. There's a lot of back and forth generally, but there's I guess there's the hard way and the easy way, right? The hard way is if we get a customer that sends us a schematic in PowerPoint. Um, that's the most difficult, right? Because then we have to kind of convert that to a schematic. And while we can use Canvas to share that schematic with them, it becomes difficult for them to, modify the schematic and convey kind of their updates and thoughts, right? So usually it's just a very iterative design cycle. There's a lot of back and forth. We do a lot of novel designs, so that always requires slight changes, things like that. I think to the point of this presentation, what's most important, even if you make changes to your schematic, is to always say, let's review the schematic, let's make sure that it still fits into the overarching system. And then whatever layout we end up with, let's still compare it to that schematic, because they still need to match. It's okay to change the schematic, but they still need to match. And then, of course, the easy way is if our customers have IPKISS, we can just make modifications to the same Canvas file, such that, if they want, I don't know, a different modulator or a Y splitter instead of an MMI, or I don't know, some change, right? Insert change here. They can then just send that Canvas file to us rather than having to, make sure all of the PowerPoint shapes are connected to the right things. And then we have to interpret that and convert it to a schematic and then convert it to a layout. So perhaps there's not a clear-cut way of doing it right now, but I hope that as this kind of ecosystem matures and as we introduce these new capabilities into IPKISS and Check Mate, it becomes essentially, there's no reason to do it in PowerPoint anymore, right? We just all go right to IPKISS for everything.
That's a nice vision. All right. Well, thanks very much. We're a little bit over time, so thanks to everyone that attended. If you have any questions or you want to get in contact with me or any of the speakers, please reach out afterwards. There'll be follow-up emails. You can reach us through our website. I know the same is true for Spark and Tower as well. So thanks for attending and enjoy the rest of your days.